Lesson 2, two-dimensional momentum questions. In fact, everything I do for the rest of the unit is really going to be building on this concept. So you really want to focus and pay attention. In terms of formula sheets, we're going to be using the law of conservation momentum, which isn't blatantly on your formula sheet. Momentum equals mass times velocity, P equals mv, that's on your formula sheet. And we're going to be using SOHCAHTOA trig and the sine law and the cosine law. You may have those memorized from last day, or if you need your formula sheet out, that's fine. I think I covered this terminology with you last year, but once again, here is some important terminology. There are two main types of collisions, although one of those types is divided into a special subtype. The first type is what we call an inelastic collision, sometimes called a completely inelastic collision. A partially inelastic collision would be a collision where part of the objects stick together, but the objects split apart and part of it shaved off as well. We're not going to deal with that. That's yucky. So in a completely inelastic collision, the masses stick together. Sorry, I don't want to underline masses. I want to underline stick together. They stick together. A good example of a completely inelastic collision, tackling. Generally, and I'm not talking about where they hammer the guy or body check the guy, but when you wrap your arms around someone, that's completely inelastic. You stick together. Some car collisions I'll make up to be inelastic. They'll stick together. A bullet hitting a target and sticking inside, that's a completely inelastic collision. That's a good example. A little violent, but that's a good example. Catching something. If you throw a heavy weight to me and I catch it, if I catch it, it's stuck to me. That's a completely inelastic collision. Momentum is conserved. By the way, if you look at all three of these, momentum is always conserved. What's not conserved is kinetic energy. Total energy is conserved, but kinetic energy, the energy of motion, that special sub-energy, is rarely conserved. Partly elastic is where the masses bounce off each other. The way I gave you, I think, last year to remember this, Nikki, is I think elastic band, rubber band bounce, they bounce off. Inelastic, not elastic. They don't bounce off. What's the opposite of bouncing off? Stick together. I don't think I talked about perfectly elastic collisions with you last year. This is a special type of elastic collision. A perfectly elastic collision has a bunch of criteria. Kayla, I include this because it used to always show up as a multiple choice question on the provincial exam, where they would tell you the collision was perfectly elastic, but they wouldn't give you much information. In fact, they wouldn't give you enough information to solve the collision, and kids would freak. But because they had said it was, magic word, perfectly elastic, there was a bunch of assumptions you could make. In a perfectly elastic collision, kinetic energy is conserved. Masses still bounce off each other, but Liam, they bounce off each other in a special way. They rebound apart at a 90-degree angle, which means if they don't give you a picture, you sort of know the picture. Both objects must have the same mass. So if the question tells you that the collision is perfectly elastic, you can assume the angle is 90 degrees. Having said that, I've underlined it. I think in your homework, I give you a perfectly elastic collision. I've decided I'm not going to be that specific on a test. To me, I hated this question on the provincial. It was so stinking obscure, and I had to have kids memorize, and you already know I hate memorizing crap. Had to memorize all this obscure data. Oh, perfectly elastic, the masses are the same. The angle is 90 degrees. You really need to know the difference between elastic and inelastic. It's just that you'll see often the question will talk about a partly elastic collision. That's their way of saying, well, it's not perfectly elastic, so you can't use conservation of energy to solve this. Little video exercise. See if you can decide which car has a larger mass in the following collisions. We're going to watch them with no sound. Well done. Let's go 2D. Example 1. Drake, my friend, what word is bold fonted in example 1? What's the first word that's in bold font? What's the second word that's in bold font? We have different directions. This is going to be ugly. Although this is going to be right angled, but I'm telling you what you want to start looking for now are where there's different directions, not just east and west, not just north and south, but directions that are at right angles to each other. Or if you see pictures like this where you know, hey, there's definitely angles here. This is what we're going to get to eventually. But let's start out here. It says this. A hockey player traveling towards the north collides. There is a collision. This is a job for conservation of momentum. With a hockey player traveling towards the east, the two become tangled together, inelastic. With what velocity will they move off after the collision? Drake, we're going to start out exactly the same way. Is this a collision? Say yes. Yep. This is a job for the law of conservation of momentum. So I'm going to write out the total momentum beforehand has to equal the total momentum afterwards. That hasn't changed, Ty. Drake, I'll call this guy mass 1. I'll call this guy mass 2. We've done that before. You can call it mass A, mass B, whatever you want to call it. Before the collision, Drake, what's moving? Mass 1, mass 2, both, or neither? Both. Stuck together before the collision or separate before the collision? So I'm going to write this. Mass 1 initial and mass 2 initial. Wham! They collide. After the collision, stuck together or separate? I'm going to argue, Brendan, so far this has been identical to Physics 11, and now we're going to pause. Brendan, my friend, are there angles? Are there directions? Are we not in a nice straight line? We have to do something about that. And our strategy is going to be dull. Sort of. What I'm going to do, Julie, is underneath each one of these, I'm going to draw its vector. So momentum 1 initial, what direction was the first guy moving initially, Drake? Oh, you know what? Since there's a compass here, I should probably put a little compass rose. What direction was the first guy moving, Drake? I'm going to draw an arrow pointing north, and on that arrow, I'm going to put the momentum. What's the momentum? Momentum is what times what, folks? Mass times velocity. Are you okay? I'm going to go 60 times 20 in my head. I'm just going to label it with 120. That's a picture of the first guy's momentum. Plus, I'm going to add these, but they're vectors. How will I add vectors together? Well, I'll draw them a certain way. Hopefully something has come to mind. What's the momentum? What direction was the second guy moving? Going to be this way. How big? Mass times velocity, 50 times 1. And that equals, I have no idea. I'll put a little question mark there. But I got two vectors. I want to add them together. How would I add them together? Draw them tip to tail. Now, I'm going to try and draw this roughly to scale. This is not to scale. This 50 should be less than half as long as that guy. So I'm going to draw the 120 pretty big, yoink. And I'll draw the 50 less than half as long as the 120. There's my tip to tail. What's the resultant from the tail of the first to the tip of the second? The resultant, what I'm trying to look for, is that. This is the momentum of both. Is this a right angle triangle? Yay. Will it always be a right angle triangle? No. Will it usually not be a right angle triangle? Usually not. But for now, we can Pythagoras and SOHCAHTOA this. If I want to find the momentum of both, I'm going to go momentum both squared equals 120 squared plus 50 squared. The momentum of both, I think I made this one actually work out evenly. Double check me, but I think you're going to get 130 when you go 120 squared plus 50 squared, square root. Kilogram meters per second. That's the magnitude, not the direction. That's the magnitude of the momentum. By the way, Drake, did this question want me to find their final momentum? What did this question want me to find? How do I find a velocity if I know a momentum? Is there an equation that has a momentum and the velocity in it? Now I'm going to go velocity is the momentum divided by the mass. So the velocity is going to be 130 divided by both masses. What were the masses? Was it 60 and 50? Why both masses? Because they stuck together. Yes? This gives me the speed, not the velocity, the speed. Now I'll need a calculator. 130 divided by 110. You get 1.18 meters per second? Or am I wrong? Yeah? That's a speed. Did this question want me to find the speed, Drake? Say no. No. What do I want me to find? You didn't say the word speed. Oh, how do I turn a speed into a velocity? Well, velocity is a vector. It has both magnitude, which I have here, but what else does it have? Oh, at. What's the direction? Let's go back to my vector diagram. See that lovely triangle right there? I guess the direction would be this angle right there. By the way, that angle, north of south, east of west, what of what? It's going to be east of north. Okay? Heck, I'll even write that. Space, east of north. I need to find theta. I think in this case, I can go opposite, adjacent, and I can use tangent. Also, since I know this, I could use sine or cosine too, but I'll use the data that they gave me if I can. Tan theta equals opposite over adjacent. (22.6 degrees). East of north. This is what we're going to be working our way towards. We start out the same way with the law of conservation momentum. We still write a momentum vector equation, but then we realize, okay, directions matter. I can't just let one would be positive, one would be negative. I have to draw pictures, and I'm going to add stuff tip to tail. If we're lucky, Simone, right angle triangle, Pythagoras, SOHCAHTOA, probably we're not going to be so lucky. Then that's going to give us the momentum. To find the velocity, we'll have to divide by the mass. That's only going to give us the speed. To find the velocity, we're also going to have to find a theta. It's a lot of small, complicated steps to get an answer. And the right-angled ones are the easier ones. Let's try another one. A car weighing 1,500 kilograms moving at 12 meters per second due west collides with a 2,400 kilogram truck that is moving at 15 meters per second due north. You know what? I would underline north. I would underline west. I would write a compass rose, and I would start to say, ugh, this is going to be a lot of work. Assume the wreckage sticks together, inelastic. With what velocity does this? Okay, they want me to find the final velocity. Is there a collision? Yep. Well, that's a job for the law of conservation of momentum. Before the collision, what's moving? I'm going to use the letter C for car and T for truck. You could use mass 1 and mass 2, but I'll use C and T. I think we're going to have the car and the truck. Yeah? Wham! They collide. We'll need to give Robbie something after this unit because he is providing entertainment and stimulation for us as we're learning, so it's all important. Helps you pay attention. Are we in a nice straight line? No? Ugh. Let's dope. Sinead, what direction was the car moving? So I'm going to draw a picture to the west. And its momentum was, how do I calculate momentum? Mass times velocity. You can, if you want to, write the 1,500 times 12 on there. Some people like doing that. If you want to, you can just go 1,500 times 12, which I think gives you 2250? 18,050. 18,000 even? 18,000, okay. And 1 8 with 3 zeros. You can just put that straight on there if you want. I always do want to put some kind. I prefer to put the actual value on there because it gives me an idea of which arrows are longer, which arrows are shorter, so that when I draw my picture, I'm roughly to scale. Plus, Sinead, what direction is the truck moving? North. What's its momentum? 38,000? 38,400? Yeah. By the way, do not round off on these because now you're using error to find error. Here I would carry as many sig figs as I could. And that equals the momentum of both. I have no idea what that is. I'll put a question mark there. Sometimes they'll give you a lovely picture and you'll know what that's supposed to look like, and you can draw an arrow at least in roughly the right direction. You won't know how long it is, but you can say, I think I'm pointing that way. Meanwhile, I have two vectors. Rebecca, how would I add these two vectors together? Draw them. Okay, so I'm going to go. Now I want to go west and then north. So I'm going to start down low so I can go 18,000 west. 38,400 is a little more than twice as long as 18,000. So I'm going to draw north a little more than twice as long, maybe about like that. That's 38,400. The resultant, the momentum of both, is that vector right there. That's the momentum of both. Sinead, is there a lovely right angle? Oh, thank goodness. Pythagoras says momentum of both squared equals 38,400 squared plus 18,000 squared. By the way, the most common mistake, I am on your test, the vast majority of the written questions, if not all of the written questions, are going to be at angles. And Simone, the reason I'm doing this big song and dance is I have kids that write this line and then they just go MV plus MV equals M both, and they solve it algebraically like we've been doing in Physics 11. And I have to give them a 0 for all of the rest of the work because it's garbage. The max you can get, I think, is 1 out of 7 if you do that, because I'll give you 1 mark for at least recognizing it was conservation momentum. And usually when I mention to those kids afterwards, like, oh, I didn't do angles, like it's throwing away marks. I think I'm going to get a yuckier decimal this time. I doubt this is going to work out evenly, maybe. 38,400 squared plus 18,000 squared, square root. I'm going to write 42,409, but I'll keep this number on my calculator. $42,409. This isn't what they wanted me to find. What do they want me to find? Velocity. If I know a momentum, how do I find a velocity? Divide by mass. So the velocity is going to be 42,409 divided by the first car and, what was the second car? 2,000? 2,400. Divided by 1,500 plus 2,400. That's the speed, 10.9. This question did not say find the speed. What did this question say? Find the, how do I turn that into a velocity? I need a direction. The direction is always where your vector is originating from. So I'm not going to put theta up here where it's pointing to. It's where it's coming from. Theta is going to go right there. By the way, that theta, North of south, east of west, what of what? That's going to be start out going west and go north of west, right? So it's going to be north of west. Let's find theta. I can go opposite, adjacent. I can say tan theta equals opposite over adjacent. Hang on. Shift tan of 38,400 over 18,000. You get 64.9 degrees. I'd take 65 degrees to 2 sig figs. That also kind of looks about right in my picture to scale. If I got 10 degrees, I'd be nervous because I've drawn my picture to scale, and it does look like it's above 45. Yeah? So 64.9 degrees. Yeah. Yep, I'd take that totally. I just tend to write the first thing that they gave me first and the second thing that they gave me second if you're ever looking at my answer keys, but I'll always take both. And yeah, for all of these, there's always going to be 2 ways you can draw this. So I'll always take the 90 minus this answer and then flip these 2 letters around. Yep. Let's kick it up a notch. Let's do a non-right angle one. Example 3. Usually, they'll give me a picture for a non-right angle one. I will always give you a picture on your test. I don't always give you a picture in the homework because these pictures are a pain to draw, and I want the homework to be tougher than the test. And so sometimes I'll actually just give you everything as how many degrees, what of what, draw the picture yourself. But here, a puck moving at 1.2 meters per second to the right, collides obliquely. This word obliquely is the fancy word for at an angle, not in a nice straight line. It's not a head-on collision. They glanced off of each other. It was an oblique collision. With an identical stationary puck, okay, the masses are the same. Puck B then moves as shown. It looks like puck B goes downwards. You know what? Let's put a compass rose here, and we can call it south. Let's say that puck B is moving south, and it looks like it moved south at 0.9 meters per second, 29 degrees that way. Oh, and from the picture, James, it's pretty obvious. I guess puck A ended up going north and east. You okay with that? James, my friend, is there a collision? Say yes. You know what this is a job for? The law of conservation of momentum. The sum of all the incoming momentum equals the sum of all the final momentum. James, I'm going to call these masses A and B since that's what they did. You okay with that? Before the collision, James, my friend, what's moving? Mass A, mass B, both or neither? Both are moving, so there's a velocity drawn on this thing here right now. And by the way, what word is right here? Stationary? Yeah, okay. So don't take this wrong. That's a sloppy mistake we can't make. We do have to be able to translate the question carefully. So I'm going to ask you again, before the collision, what's moving? Puck A, puck B, both or neither? Puck A. So I'm going to write momentum of A initial. You ready? Wham, they collide. There you go. You're doing big boy things now. After the collision, James, what's moving? Puck A, puck B, both or neither? Stuck together or separate? So I'm going to have this. Puck A final, momentum A final, momentum B final. Are there angles? Yeah. So don't be doing algebra now. We're going to dulp. I think, James, we can safely say puck A's initial from the picture looked like that. Yeah? Can someone go mass times velocity, 5 times 1.2? What's my initial momentum as a magnitude? 6. When they collide. I don't know, puck A, the final momentum is a total mystery, but I do know it looked like that, so I'll call this momentum A final. They did give me that in the picture. Plus, I know a lot more about momentum B. Momentum B apparently went down at an angle of 29 degrees?
Yes, sir.
And I can fill in how big this is. What was the mass of puck B? They told me identical, so what was the mass of puck B? 5. What's its velocity? 0.9. So can someone go mass times velocity here? 4.5? You okay with where the 6 and the 4.5 came from? By the way, another common mistake, kids just start adding velocities vectorially. No, velocity is not conserved. Momentum is what's conserved. Momentum is what we can add together. See the right hand where I have 2 vectors with a plus sign between them? I want to add them together. How should I add them together? Draw them. I'm going to draw that up here. So I'm going to get this. Mystery momentum A final, I don't know. But here's the important thing, Ty. I know that when I draw momentum B, I know what they added to. They added to momentum A, that's 6. Which means I know I'm going to stop drawing momentum B right about there. There's where I'm going to put the 4.5, and that allows me to say, there's the 6. You okay with that? I have to do some trig. This angle here is 29 degrees. It's not in my triangle, unfortunately. Okay? This angle here is going to be 29 degrees. Now, some of you may have seen that. It's a geometry thing called alternate interior angles. What you can look for is if you ever have a letter Z like that, this angle and this angle are the same. I'll do a quick proof with you. I'll show you what I did in my head. In my head, don't write this down, I dropped a perpendicular line right there in my head. This angle is 90, so if this is 29, I said this here has to be 61. That's 90, this is 29. Unfortunately, I will not always be able to give you nice angles in your triangle. Sometimes, Kayla, when you draw the triangle, the angle will end up inside the triangle. Yay! Not always. Not always. Is this a right angle triangle? Everybody say no.
No.
Sine law?
No.
Cosine law. By the way, side, angle, side. Cosine law. This is going to be cosine law. What's the cosine law going to look like? Here's what I'm trying to find. Here's the angle that goes with it. So it's going to be this squared equals this squared plus this squared minus 2, this, cos that. And I realize for those of you watching at home, a lot of this is and that. But that's how I put it together. So Sarah, it's going to be mystery final momentum squared equals 6 squared plus 4.5 squared minus 2 times 6 times 4.5 cosine 29. Yeah, this is a job for my calculator. 6 squared plus 4.5 squared minus 2 times 6 times 4.5 cos 29. 9 point, square root. Because this is momentum squared. And I'm going to get 3.00342, and I'm going to carry some extra sig figs, because this is not the answer. I'm going to use this to find the answer still. So I'm actually going to write the final momentum magnitude of object A is 3. What did I say? 00342. That's the momentum. It's not what they asked me to find. Sam, what did they ask me to find?
Final velocity.
How do I find velocity if I know momentum?
Take the mass.
What about the mass? Divide by the mass. Okay, so now I'm going to use, I know that momentum is mass times velocity, so velocity is momentum divided by mass. That's sort of on your formula sheet, but not getting the V by itself. So the velocity is going to be, and if you do this in your homework without showing this, without showing your work, Drake, like if you go straight to your calculator, I'm fine. But in our notes, let's write down that we're going to go 3.00342 divided by the mass. Let's show that so we know when we're studying later on, Tori, what the heck we did. And I get 0.6001, sorry, 0.601. Sam, am I done? Say no. You know why? I found the speed, the magnitude. What did you want me to find? What did the question want me to find? I need an at. Let's go back to my vector triangle. The at is where your vector is originating from. The theta is where your vector is coming from. The theta goes right there. This is not tangent. It's not cosine. This is not a right angle triangle. However, I now know what this is. This was, what was it? 3.003, which means I now have a pair. I can find theta using the sine law. I can find theta by going the sine of the mystery angle theta divided by what's across from it is equal to the sine of the angle that I know divided by what's across from it, which was 3.00342. Not the velocity, the momentum goes there, because the momentum is what's on my triangle. Yes? I am using the sine law. Yep. You could go this squared minus that squared divided by 2, negative 2 times this. Yeah, whatever. Okay? And then shift coast. I use the sine law because it's quicker. Now, the sine law has that problem I taught you about last day, that ambiguous case. But that's only going to be the case if the collision somehow goes like this way and that way, which I'm not sure is necessarily going to happen. Like collisions are going to be at glancing angles. Yes?
It seems as though you can use the cosine law for pretty much everything we've done so far. Is that going to be the case throughout the unit, or are you ever going to need to use a sine law over the cosine law?
I have one question in mind. I know I solved that question using the sine law because it's quicker, because they gave me extra information. But it's possible that you could also use the cosine law to solve it. I can't remember. It's going to be in a couple of days. So the answer to your question is, I think you can use the cosine law to solve almost everything, but there might be one weird exception.
Okay.
And I get a theta of 46.6 degrees. What of what? North of south, east of west, what of what? Let's try another one. These are tough. Don't kid yourself. Curling stone is a good example of conservation momentum, very little friction, so your answers actually be good. A curling stone is sliding along the ice, but it hits a stationary, James, I'll probably underline the word stationary because that tells me something, 18 kilogram bucket of sand. After the collision, the curling stone's velocity is 3 meters per second east And the bucket has a velocity of 2.3 meters per second, 43 degrees south of east. What was the initial velocity of the curling stone before the collision? Ooh. Wow. Let's come back to that. This one doesn't have a picture. Let's do example 5 first, which has a picture. Then we'll come back and do example 4. I might do example 4 next class. Example 5 says, find the final velocity, magnitude, and direction of object B. Wow, Mr. Duick, that's a terrible diagram. I know, these are a pain to do. It looks like, James, I have an incoming mass of 12.1 coming in at 9.3 meters per second. You know what? Let's put a compass on here. Due east. It looks like the incoming mass bounces downwards, southwards, glances off, and the stationary mass, because VI was 0, apparently glances or bounces or heads off northwards and east. Okay. Is there a collision, Robbie? This is a job for conservation of momentum. Before the collision, Robbie, what's moving? Mass A, mass B, both or neither? Would you like to do it? You sure?
Wham! They collide!
Wham! They collide. Thank you, Connor. After the collision, Robbie, what's moving? Mass A, mass B, both or neither? Stuck together or separate? Separate. So I'm going to have mass A final, momentum A final, momentum B final. Ty, can you see there's yucky angles and things in here? So don't start going MV and just divide and algebra like we did last year. We're going to dulp. Looks like momentum A initial looks like that, and it's going to be 12.1 times 9.3, and I'm going to carry every sig fig. I'm going to write 112.53. I'm not rounding off here. Wham, they collide. Looks like momentum A goes this way. There's a little 51. I was writing the velocity there. 51 degrees. And it's got a mass still of 12.1 times 4.1. $49.61. Again, the most common mistake I see, and unfortunately I got to start giving zeros for everything. Kids do this. They go, oh, 112.53 minus 49.61. Oh, the other object must have 62.92 because Mr. Duke momentum is conserved. No, it's conserved here. It is, but it's vectorially. We're going to be doing some trig. It's not straight, add them up. If they were in a straight line, we could do that. They are not. Momentum of object B, I don't know, but I know it looks like that. Robbie, see the two vectors that are on the right-hand side being plussed? How can I add those together? And I know that the resultant is going to be a nice straight line because that's the incoming. That's where it all came from. I'm going to draw my big vector triangle here. I do encourage you, draw your triangles fairly big. If you try and draw them small, it just gets tough. So I'm going to put mine here. I have 49.61 mystery, 112.53. This time the angle did end up inside my triangle. Yay! I don't think this is a right angle. It looks like it's close. Can't assume that, though. And also, my diagram scale, Joss, might be totally out to lunch. I don't know. So, non-right angle trig. Sine law or cosine law? Cosine law. And it's going to be this squared equals this squared plus this squared minus 2 times this, cos that. I realize there's a lot of pronouns in that sentence, but... momentum of object B final squared equals 49.61 squared plus 112.53 squared minus 2, 49.61, 112.53 cos 51. By the way, you can do this with components. You would divide each of those slanties into a east-west component and a north-south component. You would make a chart and you would track all of your east-west momentum and make sure that what you had before the collision equaled what you had after the collision. You would make a chart and you would track all of your north-south momentums and make sure that everything you had before the collision, which is 0 in this case, equaled everything you had after the collision. And you would end up with a final momentum east-west, and you'd end up with a final momentum north-south. Then you would add those two together tip to tail and uncomponentize. And this is why I don't do the component method here. It's doable, but it's just really cumbersome. Instead of 5 lines, you're up to about 12 lines. You know what? Suck it up and learn the sine law and the cosine law, because they're handy. Cos 51, you get 8,097, and then don't forget to square root. Do you get 89.987? I'll round off to there, 89.987. What did I say? 987? Of course, that's the momentum. I want the velocity of object B, so I'm going to take that 89.987 and I'm going to divide it by the mass. There it is in the picture, 4.2. Now, if I gave you this question, sometimes as a multiple choice question, I'll only ask you to find the speed, which means you could do this and quit. Or sometimes, James, and especially in the big review that I gave you, they'll only ask you, Andy, to find the direction, which means you actually wouldn't need to find the velocity. Once you had this number, you could stick it on the triangle and go sine law or cosine law and just find theta. But for now, I get 21.4. At. I got a problem here. I mean, I'd sort of, don't write this down, I'd sort of like to put the theta there, because that's where it's coming from, don't write that down. The problem is, that's a nothing of nothing. It's a slanty next to a slanty. Doesn't help me. Any thoughts on what I can do? Okay, so here's another step that makes these tough. All of you right now, could you add a little dotted line like that? A nice horizontal dotted line. Put a theta right there. I'll use that. Now, if I draw that in, Brendan, that theta is going to be north of south, east of west, what of what? Hang on. Sorry? Go ahead.
Why can't you just put the theta inside the triangle?
Here?
Yeah.
What of what?
So you know the PB.
I know the PB, but what of what? How would you describe that theta? So let's suppose that theta worked out to 71 degrees. 71 degrees, what of what?
West to south.
No, it's not west. That's not west. That's not south. It's just hanging midair.
Sorry for the interruption, but during flex, can the following...
So Connor, this is not beside any horizontal or vertical line. The horizontal or vertical compass lines are a reference. So we have to do this. And then, see the Z? That angle is going to be the same as this angle. Now this angle is the magnitude that I want, but this is the direction that I want. What direction is that? North of east, I think. Yes? So let's add a little north of east. Your homework, by the way, folks, is just going to be the take-home quiz. I'm not going to assign any questions yet. Next class, I'm going to continue on, and I'm going to give you lots of practice on this, okay? How can I find this theta here? It's going to be the sine law. The sine, let's do it in red so it stands out, of my mystery angle theta divided by what's across from it equals the sine of the angle that I know, 51, divided by, and as Connor did point out, I now know PB. It was 89.987. Get the sine theta by itself. It's going to be multiply the 49.61 over. It's going to be 49.61 times sine of 51 divided by 89.987. Shift sign of that. And yeah, the cosine law I think would work there too, but I have to double check. 25.4 degrees. Your homework, take-home quiz, please.